What is the amplitude of this wave? Calculate this wave's frequency. Plot the displacement against position of two wavelengths of a wave with an amplitude of 1 centimeter and a wavelength of 40 centimeters. Plot the voltage against time of a wave with a frequency of 4 Hz and an amplitude of 3 volts. A wave is plotted on an oscilloscope over 0.6 seconds and produces a trace looking something like this. What is the amplitude of this wave? I've drawn a bit of a hint on the diagram here, showing you the maximum and minimum displacement of the wave. So the question really, is the amplitude the distance between the maximum and the minimum displacement? Or is it the distance between the maximum displacement and the rest position in the middle? Well, the answer is that it's the displacement from the rest position. So our amplitude here is 2. The rest position is the position of the particles before they're disturbed by the wave. So they'll be sitting in one position, and then after being disturbed by the wave, they'll start moving up and down. So they'll end up above and below that position. Question 7. Calculate this wave's frequency. Now what we're given here is a graph of displacement over time. And that means that we're able to measure frequency and period just by measuring properties of this graph. So we can see that there's a 1 second over here, and the frequency of a wave is how many wavefronts pass through a particular point over 1 second. So if we were to measure the number of wavelengths in 1 second, we'd be able to find the frequency of the wave. We can see that there's 1, 2, and a half wavelengths altogether, right? So this is one whole wavelength. This is a second whole wavelength, and this bit at the end is only half a wavelength. So our answer is that the frequency is 2.5 Hertz. We could also figure this out by measuring the period of the wave. That's how long this interval is of one wavelength, and then taking 1 and dividing it by that wavelength. We will, of course, get the same answer of 2.5 Hertz. And that brings me to the next question. What is the period? Now it turns out, because we already have the frequency, we can calculate the period just by taking 1 and dividing it by the frequency. So doing that, we take 1 over 2.5 equals 0.4 seconds. So that means that this point on the graph over here is 0.4 seconds. And after a second wavelength, we'll be up to 0.8. After half a wavelength, it'll only take half this time, so we'll only be adding 0.2, which brings us all the way up to 1, exactly what we see on the graph. Find the amplitude. Now remember, the amplitude is the displacement of the particle in the wave away from the rest position. The rest position is this 0 on the y-axis, and so we can see that our amplitude will be, that's right, 0.4 centimeters. Finally, find the velocity given that its wavelength is 50 centimeters. So that means that if we were to look at the wave as a whole and as it traveled, then the distance between two successive crests would be 50 centimeters. So how do we find the velocity of the wave? Well, we know that it travels one wavelength in 0.4 seconds, and we know that one wavelength is 50 centimeters long. So our speed is 50 centimeters over 0.4 seconds. Of course, the other way we can do this is, instead of taking distance over time, we can simply say distance times frequency, because frequency is 1 over time. So we use our equation, v equals f lambda. We put in f 2.5 and lambda 0.5 meters, and we end up with 1.25 meters per second as the speed of the wave. Plot the displacement against position of two wavelengths of a wave with an amplitude of 1 centimeter and a wavelength of 40 centimeters. It's a bit of a handful. Now, displacement versus position says that we're not plotting anything against time, so we don't need to say how the wave changes. We're simply giving a freeze frame or a snapshot of what the wave appears to look like at a particular point in time. So on the x-axis, we'll have where along the wave we are. And so the wavelength there will be 40 centimeters. We're drawing two wavelengths, so the x-axis will have to be at least 80 centimeters long. If our amplitude is 1 centimeter, that means that our maximum displacement away from 0 is 1 centimeter up and 1 centimeter down. So our graph looks something like this. We can see that on the x-axis we've moved up from 0 to 80, and it's taken us two wavelengths to do so. One whole wavelength, and then two whole wavelengths. So a wavelength is 40 centimeters. We can see the displacement of the wave goes all the way up from 0 to 1, and all the way down from 0 to -1. Question 9. Plot the voltage against time of a wave with a frequency of 4 Hz and an amplitude of 3 volts. So in this case, we're measuring the amplitude not in centimeters, but in volts, which doesn't actually make anything that much harder, don't worry. Now we're plotting the voltage versus time, which means that we look at a fixed point of the wave and show how it varies up and down over time. So if it has 4 Hz, that means that in 1 second, 4 whole wavelengths will pass through the particular point that we're looking at. So our graph will look something like this. We can see that in 0.5 seconds, we have 2 whole wavelengths. That means that in 1 whole second, we'll have 4 whole wavelengths. The other way we can look at this is by finding the period of the wave, which will be 1 over 4, 0.25. We can see that if we look at the period of the wave here, which will be 1 whole wavelength, then it's, as we would expect, 0.25. Our amplitude has to be 3 volts, which means that our y-axis will be plotting voltage. And once again, we can see that it will go from 0 all the way up to 3, and all the way down to -3. Question 10. A wave is plotted on an oscilloscope over 0.6 seconds and produces a trace looking something like this. Find its wavelength. Now what we're given here is position and voltage, right? So we're looking at a freeze frame after 0.6 seconds, and we're given this wave. That means that we can find its wavelength by measuring the distance between two successive crests, or 2 points in the same pattern of the wave, like these points here. Can you see why that works? At both these points, the wave is at its maximum slope, and we're at the same part of the pattern. We're heading up toward a crest. So these two parts of the wave are identical. The other two parts of the wave that we could look at, this part and this part, for example. So in both of these cases, we're halfway through, heading down from a crest to a trough. And in both cases, of course, the wavelength is going to have to be the same, and we can see pretty easily that that's going to be 1 centimeter. All right, calculate its period. This will be a little bit harder. So to calculate its period, we'll have to know what's given to us in the part of the question here. The wave is plotted over 0.6 seconds, and in that time, we get 1.5 whole wavelengths. So that means that over 0.6 seconds, we get 1.5 wavelengths. And if we want to find its period, then we need to figure out how long it would take for just one wavelength to go by. So essentially what we need to do is take 0.6 and divide it by 1.5, and then multiply it by 1 wavelength. So 0.6 over 1.5 will give us the time that it takes for a single wavelength to travel across, instead of 1.5 wavelengths to travel across. And that, of course, will just give us 0.4 seconds, which is 2/3 of our original value. We can see in this trace that 2/3 of the trace will be 1 whole wavelength. Find the frequency. Well, now that we have the period, the frequency will be pretty easy to find. That'll simply be 1 over 0.4, which gives us 2.5. That means that every second, 2.5 wavelengths will pass through a particular point. Finally, find its velocity. Now, how would we go about doing that? Well, we can use v equals f lambda. Our frequency is 2.5, and our lambda wavelength is 1 centimeter. which of course is equal to 1/100th of a meter if we're using SI units. So we take 1/100th, we multiply it by 2.5, and what do we get? Well, we get, of course, 0.025 meters per second, which is the same as 2.5 centimeters per second. Right, well, that brings us to the end of the questions, which means that we've finished our section on graphing waves. In the next section, we'll be looking at more detail in a particular kind of wave called the sound wave.